Welcome to the lecture number 6, I think. So we will have 90 minutes lecture. Then we make a small lunch break, and then we will go into the seminar. And we have a very special paper today. I ask you to prepare, because this paper will be subject of the seminar for multiple sessions now, because I want you to scale up the process. And today we will just discuss the paper as we discussed it the other time. So you should be able now to read these kind of papers. And then I will give you some tasks about how to really make something out of the information in the paper, how to make a company out of it, and all these things at the end. I think it's a quite nice paper for the class and also for the idea of the class. And for today, as you see, I had to change a little bit the schedule, because we took a little bit more time in transport, but transport is so important for me that I took this time, because this is one of the things you really, really should take out of the class, how particles move. And this is why we took an extra lecture on transport, but this is not really a problem, because here you see that one thing is left out now, but I can include it very easily into these experimental methods. So we will not have much loose at this point, but I think these 4 blocks of transport are really fundamental. Do you have any questions regarding the homework? Because your homework is online now. I needed a little bit more time because of the free day, but I gave you the extra time, so you have 1 week to do it, right? And then you upload it on Ilias. Did you found where to upload? Okay, because everything is, so if you have questions, now is the time, not when the deadline is over. When the deadline is over, it's done, okay? If you have questions now or tomorrow, not afterwards. Afterwards, it's done. Okay. Good. So we will finish transport, and then we will go into a new topic next week. And for today, again, the promising empowerment. So again, why is moving important? And we will still work on diffusion and force balance. And this is something you will hopefully see, because again, I will try to make a technical applications toward this. So we will repeat again what you should know by heart now, but again, apply it a little bit differently. So what did we do last week? Who remembers what we did last week? Yeah. Mm-hmm. 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 Sorry, the last one?
And finding another base in order to overcome the extensiveness of vacuum.
Okay, very good. So chemical vapor deposition, and then the atmosphere in chemical vapor deposition, where we need vacuum, or we try to go to atmospheric conditions, but then we have to deal with the situation, because the best for your reactions would be vacuum. There were also a few of you which mentioned that you already did CVD in the lab, and you also afterwards corrected me, because I was a little bit puzzling about it, because the layer you grow in CVD was 200 nanometer. Yeah, and this makes more sense than the millimeter, because this is what you normally do with CVD. So there is lab classes here where you can learn this. Okay, what else? CVD, what else did we talk about? Yeah? Mm-hmm. 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 Thermophoresis, right. Thermophoresis. Yeah, right. Mm-hmm.
Preventing the deposition of particles in clean room.
Mm-hmm. Very good. Okay, so you mentioned multiple points. So atomic layer deposition. What is the difference from chemical vapor deposition to atomic layer deposition? We talked about this. Or is it the same? Yeah?
Like in atomic layer deposition, the deposition takes by
Mm-hmm.
by layer.
Very good.
Chemical, like it's not by atom, it's like
It's just growing. Okay, so you have a precursor, the precursor react, the more precursor, the more reaction, the more growth. And as you mentioned, in atomic layer deposition, you grow layer by layer by layer, so the precursor comes, reacts with the surface is closed, and then there is no reaction anymore. So you need a second precursor, you need to purge, and then you need a second precursor to reactivate the surface. Very good. And then we talked about, you also mentioned thermophoresis and an application. Maybe another one of you can repeat. What is thermophoresis and where do we use thermophoresis, for example? Everything you said was correct, but since I would like to see if the others also. Yeah.
This was the movement conducted by temperature difference.
Very good.
Speed,
Mm-hmm.
so that it's more important to special diameters.
Mm-hmm.
And I just remember I don't know if we mentioned that one, the application with the flames,
Mm-hmm.
and that we had a cold blower,
Mm-hmm.
it was cooled with water, so the particles all moved towards the surface.
Mm-hmm.
Set it down there.
Very good. So you have a temperature gradient, and this leads to a force. Why? Why there is a force coming from the temperature gradient, and how was this related to something we already discussed before about the transport of particles? We related. It was a very logical explanation that thermophoresis appears from the picture I showed you and from what we discussed before. Because what is thermophoresis basically, or it's the same as another phenomena we discussed in the first and second lecture of transport. Okay.
I think it's very similar to convection.
Is it similar to convection? What happens by thermophoresis? Yeah? Yeah, and to what did we relate it? I mean, there is a continuum equation and a free molecular equation, but from the free molecular picture, we explained thermophoresis. Because there was a temperature gradient and that makes something different to another phenomena. What was the other phenomena? Yeah, exactly. So basically it's nothing else than diffusion, but diffusion for particles is because of the molecules hitting the particle. But if you have a temperature gradient, the kinetic energy of the molecules around the particle is different, and this leads to a force and not like in diffusion, a random walk. Okay, and then you mentioned also the flame application. That's quite nice. So just to sum up, and then we are finished with repetition. So how do I describe basically the movement of particles? Everybody of you should know this now. Sorry? How do we describe the motion of particles very basically, very generally? Yeah? Navier-Stokes with, yeah? Diffusion, force balance, okay? Yeah, try to sum it up a little bit more. So Navier-Stokes is a force balance, and this force balance contains of?
transient, convection, diffusion, and external.
Yeah, exactly, okay? And this is the answer I want to hear in the exam. So we still stick on this equation today. And what we do is normally we one second. We take this equation, we simplify it, and we apply it for different cases. And with these cases, we can make the calculations you mentioned, for example, from the table, right? Where we can calculate different mechanisms and how good they are. So when diffusion is better than thermophoresis or the other way around, or settling. And something similar we will do here, because we will now talk about, again, diffusion and about deposition by diffusion. Okay, and there I need the board a little bit, because I would like to ask the question deposition by diffusion. What could I mean by deposition by diffusion? What is the mean? I mean, I think you understand the word, but what do you have an idea what I want to do now? Deposition by diffusion. Yeah? Mm-hmm. Mm-hmm. A build-up of layer, okay. That's a quite nice idea, but it's a little bit different what I want to do here, okay? But it's a quite nice idea. So if you think about a wall, just one wall, okay? And there you have molecules, gas molecules. And the thing with gas molecules, what happens, so if you think about your thermodynamic lectures, so you have a wall and you have a gas, what happens with the molecules and the wall? If the molecules hit the wall, what happens? Yeah? It changed the momentum, very good. And what happens with the molecule? So you have one molecule, and here's a wall, right? So the molecule goes to the wall, and what happens to the molecule? Yeah.
Passing the wall,
Yeah.
or going through the wall, and one possibility is sticking to the wall,
Mm-hmm.
and another one is collision and coming back.
Exactly, and this is the main picture we have in mind, very good. And so gas molecules rebound from the surface after collision. What entity can be measured by this? Or what phenomena or basic variable is related to this one? If you have a balloon, for example, yeah? Velocity is of the molecule, but I mean of the system more. Maybe the question is not... not so complicated, yeah, but easy, much easier. So if you have a balloon and the air molecules, they move around in the balloon, they hit the wall, they rebound. Pressure, right? So gas pressure is transferred to the walls. So this is molecules. And I mean, it's maybe a little bit simple, but always keep in mind that we are in a size range where we somehow already see molecules. Okay, 1 nanometer, 10 nanometers. So it's always extremely important to clearly distinguish the behavior of molecules and of nanoparticles. Because in this size, they show so many similarities. We saw this for diffusion, right? diffusion of nanoparticles is more or less the same in the description, in the equation, as for molecules. They diffuse, they have a diffusion coefficient. However, the phenomena is different, okay? Because it's not the pure kinetic energy, it's the bombardment. But at the end, you can use the same equations to describe. So it's always important to be very clear about your system. The difference here is that aerosol particles and this is what you mentioned when you saw, because you said there are multiple cases, right? And I fix you here to one case. And here I want to fix to the other one. Aerosol particles adhere to the surface after collision. So this is a very oversimplified picture, but we say, okay, molecules, they don't stick, they just bounce. And aerosol particles, once they move a surface, they stick. There is research which try to figure out that aerosol particles also can bounce. So it's observed that they also can bounce, and there's discussion about it, but here we keep the picture a little bit simplified, and we say that the concentration at the surface is 0. Okay, so this means that once a particle hits a surface, it sticks to the surface and it's gone. So we take it out of the game. It means that the surface is quite large and the particle in relation to the surface is very small and we just can neglect. It's not like atomic layer deposition where we look at the growing layer. We just say, okay, here's a huge wall and a small particle hits it and then we just say, okay, the particle is gone. Because if not, we have to consider this particle sitting here and makes it everything quite complicated. Okay, so the concentration at the surface is 0. No particles are on the surface. And then we can, I also can show you a very simple, no, first we make this. So the following concentration gradient causes continuous diffusion. Causes wrong. Continuous diffusion. Who can explain me this sentence? The following concentration gradient causes continuous diffusion. If you think about concentration at the surface is 0. What is the meaning of this sentence? Yeah? Mm-hmm. Mm-hmm. Yes, so if you take a look here, this is the picture I want you to keep in mind. So there is a wall, and there are particles, just aerosol particles. But very close to the wall, you see there is a very small gap. I mean, there's everywhere a gap, but they are somehow homogeneously separated. But here are no particles. So we have a gradient directly at the beginning. What do this particle do naturally? Very small particles. What are they doing? I mean, it's quite obvious from the board. Yeah?
Coming from the high concentration, low concentration.
Where's high concentration? Where's low concentration?
Solution or in
Yeah.
the environment of the surface.
Very good.
On the surface, there is concentration of zero.
Yeah.
It's a gradient.
Yeah. So, and that's what happens. So what we do is we again simplify everything. We have just one dimension. But if you remember the diffusion, the general diffusion we derived, we allowed the particle to go left and right. Now in the picture I make it up and down, but at the end it doesn't matter. But it's easier to show in this way. So the particles only move in one direction, or one dimension, sorry, so the particle can diffuse up or down. There's a 50-50 chance. And the chance is very high because we already have a small concentration gradient that they go into this direction. And what happens if a few of them go and hit by diffusion? They travel to the wall. What happens with them? So this one, for example, in 2 time steps, tuck, tuck, hits the wall. What happens? Yeah? Will it bounce back? Yeah? It adheres to the surface and then? Yeah? Sorry? Yeah, so it's gone, right? So it goes to the surface, it adheres, it cannot go back, and it's gone. So what does it mean for the particles which are very, very close to the surface? What happens after a while with them? Yeah? It doesn't form a layer. Why it doesn't form a layer? What was the explanation of? I mean, you can, but this is not how we consider it here. What happens with them? She already explained it. Yeah? Yeah, exactly. Very, very good. So we have a lot of particles very close to the wall, and by chance, they can go only up and down. I mean, in general, in reality, they can go left, right, and everything, but for the equation, it's easier to start with one dimension. And if we have everywhere the same concentration, but not on the surface, there's no concentration, particles will go there by diffusion, and they will go out. And this means that the concentration close to the wall decreases, because by chance, half of them will be away. So in the next picture, this one is not here, this one is not here, this one is not here. What does it mean for the concentration profile in these aerosol here? Yeah? Yeah, very good. And with ongoing time, what will happen? The longer the time, what will happen with the concentration? Will it be the same or? Yeah. Mm-hmm. Exactly. And the size of the zone will grow with time. Okay, because you generate a concentration profile, and this gives more a direction for your diffusion already, right? And with this, it grows, 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 and more particle will stick to the wall and will go out. So the question we have is, at which rate are particles removed from the aerosol okay, I can add this onto the surface. Okay, that would be the question here. So the particles, they diffuse, up, down, they hit the wall, they are out. And the question is how fast or at which rate are particles removed from the aerosol of the surface. So deposition by diffusion. What kind of application could this be? You already can get the idea of the application from this sentence. What kind of application could this be? I tried to just... Yeah? Coating, yes, but in coating, you have one thing, and this is neglected here. I mean, for coating, you could calculate how fast they will travel, but what you don't consider here. What is one part in coating you need, but we keep it out. But you can calculate the velocity, so it's right. But what is neglected here? Very important for the understanding, yeah?
In coating, you have nucleation at
Uh-huh.
some parts that would affect the further process.
Mhm.
But here we are neglecting.
We don't have any nucleation, that's correct, but we're neglecting something other in the model, yeah? Yeah, that's another application, okay? But the question, what are we neglecting here? Yeah? Yeah, so we have a monodispersed size, but what happens in coating? What do you do in coating? The idea of coating, yeah?
Coat the surface.
Yeah.
Or the concentration at the surface will be very high because the surface is the material.
Mm-hmm. Exactly, perfect. So it's not wrong what you, basically it's right what you're saying, but in coating you grow a material. And this growing we completely neglect here, okay? Here's no growing. Once the surface is touched, it's gone. So for coating, you could calculate, okay, how many of them I will have on the surface, but then you have to make an additional calculation, okay, how do the layer grows? That's not in the picture here, okay? And for me, it's really important for all the concepts we're discussing that you very clear can describe the models, okay? So if you say, okay, this works for coating, then I want to have the explanation that you say, but in coating we have a growing layer, and this is not in this model here, okay? So you know this from particle technology that I really want to have the importance of the models, right? So this is really something you should be aware. And another model where it works quite well is, now you can repeat again what you were saying. Yeah. Yeah. So for filter application, because what do you want? You want to remove particles. And this is exactly what a filter is doing, right? So here's a nice application in filtration. And if we now want to answer this question and keep this picture in mind, we say the particle concentration at any time at x What is x here? The particle concentration at any time at x. Yeah? Yeah. So each particle has a different distance to the wall, and this distance, because we just have one dimension, one distance, is x. So it means n, x, and t. So number of particles or number concentration of particles depends on two variables. It depends on the time, because this picture will change with time, and it of course depends on the position, because the ones which are very close to the surface, there will we have much faster a change in the number concentration, because they hit the wall earlier than the one which are a little bit away. And this must satisfy Fick's second law of diffusion. Do you remember when we had Fick's second law of diffusion already? We already had this in the lecture. Do you remember when? When did we talk about Fick's second law of diffusion? Yeah? Yeah, when we want to understand diffusion for particles in general, right? So we say, okay, we can, there we make this equality to molecules, where we say, okay, basically they behave like molecules in the way how they diffuse, and then we can describe it. Do you remember the equation? Yeah? dn to t. Okay, and then? Yeah. Yeah, it's okay. So this is number concentration, this is time, this is distance, and this is again number concentration, and this is diffusion coefficient. So this is basically how we learned diffusion in one dimension. So this should happen here also, right? Because the only thing we are changing is we have a wall. That's it. The rest is the same. So we use the same equation. And we already can say some things, and we can say that if n, x, and t is 0, then we already know n. Okay, so the number concentration, it doesn't matter at which position I am, at time 0, when nothing has diffused so far, there will be no change. So we have the starting position, n0, okay? And the second one comes from what you see on the board. At any time, how do you read this one? And what is the solution of this one? Yeah? Yeah, very good. So this is the wall. So we already have two solutions. And then we can solve the equation. And the solution of the equation is very similar to what, and now I have to don't make mistakes, to what we had already on the slides in the diffusion part. This is nxt, right? So the concentration, number concentration, anytime, anywhere, is depending on the initial concentration or the initial number concentration. Then we have p dt 1.5. Okay, diffusion coefficient, time, and the p. And then we have the integral from 0 to x, exponent minus p squared. Also, das I need later. So 4 dt. dp. And now you're wondering a little bit what is this p? And basically this p is a dummy variable which goes from 0 to x, okay? So depending on my position, this is just a dummy variable, a short trick. So p is a dummy going from 0 to x. And what I can do now is I can divide n by the initial amount of particles. And what would this then be? So I take at any time, anywhere, and I divide it by the initial. Then I get a so the concentration here is always numbers, okay? So it's the numbers of particles. So if I divide the numbers at any time, anywhere by the starting amount of particles, I get the, yeah? It's, what is the meaning? It's because, sorry, I was a little bit, so this is number concentration, right? And this is number concentration. So now you divide the number concentration at any time, anywhere, by the starting number concentration. And what is the meaning of this deviation or dividing? Yeah? Yeah. It's right. Basically, you're right, and it's the answer for the question. It gives the rate how fast the particles are removed. Gives the rate at which, okay, particles are removed. So because here I see how fast the change is. And this is what you can see in this picture here. Okay, so you see on the y-axis, you see nxt divided by n0. So it gives the rate at which particles are removed. And then we see that this is calculated for 50 nanometer particles. And who can explain me now this diagram? What do I see here? What do I see in this diagram related to what we have here? What do you think? Yeah. Very good, exactly. So how do you see the different time steps? Or can you explain what changes over the time steps? Yeah. Yeah. And we also see that this goes more into the volume, right? So it changes over time, and the longer it goes, the more particles will travel to the wall, and the more, let's say, the more, with ongoing time, you will figure out there is a wall if you're a particle, okay? So if you're a particle, and here we don't have any change in concentration, only on the wall is nothing. And after a while, the first one already touches the wall, but the particles here, they still don't know that there is a wall because they never come into touch. They don't feel the gradient, the concentration gradient, and with ongoing time, this goes, okay? And now we can go a little bit further. I have to go to the other board. And this is that we can say, okay, we can determine the rate of particle deposition per unit area of the surface by evaluating the concentration gradient at the surface and applying, and that's now the question. What can we apply? So here we have the fixed second law of diffusion to describe the movement, right? And now I want to have a wall. This is a wall. And the movement through the area. Which law is this? The flux through the area. It's, yeah? Yeah, Fick's first law. So now we can apply Fick's first law. Because if you think about, you have your wall, and now we have diffusion, which is described. And what we want to figure out is how the particles go to this wall, right? And this is nothing else than an area and the flux through this area or on this area. And then we can say the concentration gradient at the surface dN divided by dx at x equals 0. What can we say from there? We already have the equation. So I say dN dx, dN divided by dx is equal to so I would like to know at the surface, right? So I want to apply Fick's first law. I want to do it. And therefore, I first say, okay, the concentration gradient at the surface, I need a description of this concentration gradient at the surface. And from the derivation before, we have this information. What is dN dx at x equals 0? Yeah? Very good. N0 pi d t square root, right? Because this is 0. This is 0. So for x equals 0. And this I can equate now with Fick's first law. So Fick's first law is the flux equals minus d dN dx. Now you see that we can play around, and I will go here further because I need the, no, I will go to the right. I'm sorry about I need the space. So with this we could say, okay, the flux is equal to N0 d pi t 1.5. Okay? So dN dx, and then you just change around a little bit. And what can we do with this information? With this information, we can give the statement that to get the cumulative number of particles deposited per unit area of surface what do we do with it? So we have now a flux, okay? So we have a description of the particles going to the surface. And what I would like to do here is I want to count them. 1 is coming, 2 is coming, 3, 4, 5. So I just want to count all of them. It's not the concentration as I have here, but I count them, and therefore I just have to integrate this equation over which variable? Yeah, very good, over time, right? I'm staying there with a watch, and then I say I'm counting over time, 1, 2, 3, 4, or 1, 2, right? That's the difference. So very good, I integrate over time, and then I get, and that's now the large N, okay? So this is the cumulated number I counted, and if I integrate over time, I would say N0 d pi t 1.5 dt, and this leads to N t equals 2 N0 dt pi and a half. Okay, I had to catch the camera back. Good. And that's it. So what can we do? We can cover 3 boards with math. And when we do this, at the end, we have mathematical descriptions which tell us, if you think about this picture here, how many particles over time will travel to my surface and stick there. They will go to my fiber, for example. So if I have a filter, I can count now the equation, the particles coming, or I can express the change in concentration. Okay? So over time, over position. So this is the number of particles at the surface, right? This is at my wall. And this is the general concentration in the aerosol over time, and position. And you can get this picture here with this equation, or you can kind of generalize it a little bit more. And if you generalize it more, then you get this picture. So now we don't have a development over time as we have it here, but what we have here is the y-axis is the same. It's nxt divided by n0. But on the x-axis, we now have x and t as a variable. And this means that you have a very general behavior. And this is not a surprise. It's a concentration gradient, right? And you know how they look like and how it would develop over time, over position. Phew. What did we calculate here? Who can repeat what we calculate? I want to see if I lost you. Yeah? Number of particles on the surface. Exactly. On which surface? And how do they go there? On which surface and how do they go there? Very good. Very good. Okay. So the second law is the movement of the particle. It's the second law. It describes the movement of the particles, and no, but you're on the right way. Yeah, very good. So the second law is basically the movement of them, because they diffuse, nothing else. We neglect everything else. So this is the movement of the particles. We have some conditions because we have a wall, and therefore we can solve this equation. And this is movement of the particle in the special model we see here. And then we use the first law. And the first law is a flux through an area. And we say, okay, a wall is an area. So when we have a movement towards it, and with this we can count the arriving particles on the surface, okay? And this is what we do here. If somebody is interested in the project work, I really would like to have these derivations, okay? That's nothing we can do here in the class, but that's a very nice project work, to make all these diagrams with Python, and then you learn a little bit about Python, and go through the derivations. Okay, that's a very nice theoretical project work. Any questions? Good. Then I would like to show you the table, because you already mentioned a table. And this is the same table as you mentioned before for thermophoresis. Because what you can do at the end is you can calculate now diffusion to a wall. You could also calculate a velocity out of it. Okay, if you want to make a velocity out of it, so you would just take the flux divided by the number of particles, number concentration, sorry, and then you can make a velocity out of it. And this is basically the deposition velocity, what we would call. And here you see for different sized particles, after 100 seconds, so the time is fixed, 100 seconds, and now you see the wall and how many particles arrive. And what is compared here? Yeah? Yeah, the size is changing, and which mechanisms are compared? Yeah. So where did we had already the settling behavior? Do you remember where we had this question? Yeah. Exactly. When we calculated the dust particles falling down, and this is just calculated here now for 100 seconds for a given size, and for just standard density. So with what we discussed, you can calculate these settling velocities from the earlier lecture. With what we are discussing today, you can calculate this diffusion settling velocity, okay, and how many of them will arrive, and then you can compare the mechanisms. And when is, not surprisingly, what is the result of the comparison? Shouldn't surprise you. Or what can I learn from this table? Let's say it like this, yeah? Yeah, the settling velocity is increasing, or the number, there's this number, right? I mean, the settling velocity just leads to the number at the end, but here we have the number of particles. How is it changed over size? Okay, yeah? Yeah, but generally, this is correct what you're saying, but explain it generally. What can I learn from this table? Yeah? Yeah. You started wrong. No, you started right, then you made a small mistake, but at the end it was wrong again, right again, sorry. So, because, okay, it's an important point. I want to read it. How do I have to read this table, or what do I learn from this table? Yeah?
The higher the particle sizes, the lower the number of diffusion. Yeah. And settling is that much of.
Yeah, high or not? What do you say?
Settling is high.
10 to the power 7, high or not? Compared to 5. Exactly, and this is what it's really important to understand. So if you have small particles and you have a wall, it's a very simplified picture. Diffusion is extremely efficient to separate these particles. The larger the particles, the less good your diffusion is, but the better other mechanisms came, right? And the better the settling works. And this is why we have, in particle technology, we talk about it, we have sedimentation as a separation unit. Okay, it makes only sense for large one. How would you separate small particles? By which mechanism? Yeah? Diffusion, exactly. Diffusion is used to separate particles. And for me, I mean, it's a table, but for me, it's extremely important to understand that these numbers in these tables, you can make now the calculations. And if you want to try the table thermophoresis, the table here, just make the calculation, as I also asked last week, and see if you have roughly the same numbers. Because all of this comes from the theory, and there is, of course, an application of this theory, and this is what you see here, for example. this is a catalyst in a car. And a catalyst in a car is a gas flow through a tube. So now we don't have one wall, we have 4 walls. But that's it, okay? So if you look at this picture here, here's one wall here, one wall here, one wall here, one wall here. So we can use our simplified picture to understand what happens here. And the catalyst is very interesting when it comes to nanoscience. So now we go a little bit into nanoscience. Because what happens in the catalyst? Why we have a catalyst in the car? Yeah, to convert carbon monoxide to carbon dioxide. What else? Correct, yeah. Also NOx, right? There are also NOx and some others. And what you have is you have gas. And sometimes it depends on your, if you have a diesel, you also have soot particles. And this gas is flowing through the tube. And how do the molecules go to the wall? What do you think? Diffusion, exactly. And they just have a larger diffusion coefficient. So for molecules, it goes faster. But we will take a look at particles at one point. But so basically for us, it doesn't matter if an aerosol particle or a molecule goes here. We could calculate now the diffusion to the wall. On the other hand, you have this alumina wash coat. It's a very porous structure, and the wash coat is there to carry platinum or zirconia or what else, rhodium, and all these particles are there to make the CO to CO2 NOx conversion. And therefore, we need this porous structure. And in catalyst, it's basically all about to understanding the activity over the property of your nanoparticles. So in the alumina wash coat, you have the porosity, the porous structure. It's a very high porosity, and so there's a lot of room for the molecules to diffuse in, and there's a lot of room to put the particles you need for your conversion in there. So here you see precious metal on wash coat particles. And at the end, what researchers try to understand is, and this is what is seen here quite nicely, the activity over the nanoparticle size. And you see there is a huge difference if your nanoparticle is 6 nanometer or is 2.5 or 3 nanometer, okay? So, and at the end, what you want to do is you want to know which material has at which size the best activity and how can I produce it exactly in this size. Because we talked about size distributions. And now you see, okay, there is really a difference from 2 to 6 nanometer. So you have to find a method which gives you 3 nanometer particle without giving you 6 nanometer particle. And that's very tough. Atomic layer deposition can do this to a certain extent. And atomic layer deposition is used. If you make a platinum, it looks exactly like this one here, but still there is a distribution, okay? And this is a very nice example of nanoscience because you have an extreme nano effect, and this is the change of activity of size. And now you have to understand it, you have to measure it, you have to synthesize, and yeah, you have to basically know your system and produce as engineer exactly as what you want. So this is an example of gas molecules, but at the end, gas molecules diffuse and nanoparticles diffuse. Gas molecules are faster. And the wall I gave you is just a model, but this is the practical problem, a tube. Okay, a gas goes through a tube, and there we want to understand the diffusion. So a problem of great practical importance is the diffusion of aerosol particles to the wall of a tube. And to simplify, because this is a highly complex system we want to describe, we have to make some simplification. And we say, first of all, we have fully laminar flow. Okay, because you have to think about, we have a flow, so a gas flow. Aerosol is in a gas. It comes from the engine and goes to the catalyst. So it flows with the gas, but it will not diffuse in direction of the gas. I mean, there will be diffusion, but what I want to have is that these are the walls of my tube, and my particles are in here, and the gas goes just through the tube, okay? So that's the movement from the convection. And this does not lead to any separation. So in the same way, I have this movement, and then the equation gets, you can imagine now that the equation gets a little bit more complicated, because you have the convection part, but they also diffuse at the same time. So I have both effects. And diffusion is the effect which leads my particles to the wall, right? But I only have a limited time, because if I'm too slow, they are already out. Go with the convection. Okay. So, and to have a good description, I need to have an understanding of my flow, and this is why this is solved for laminar flow profile, okay, not turbulent flow. And the second one is the tube having a cylindrical cross-section. So it means I have a small cylinder, a perfect sphere, no, a perfect circle, and this is just going through. And with these assumptions, we can introduce something called deposition parameter. So this deposition parameter tells me something about my deposition, okay? This is something we can introduce if we make all the calculations. And this deposition parameter depends only on three things. So it's something very easy to calculate. And it depends on diffusion. High diffusion means high deposition. It depends on the length of the tube. Why the length of the tube? So you can imagine a high deposition parameter means a lot of particles are deposited, right? So this is how we have to interpret it. Why the length of the tube increases the number of deposited particles? Yeah? Yeah. Yeah. So it increases the area or the time. The particle has more time to hit the wall, right? But it increases the area. Very good. And on the other hand, we have a volumetric flow rate. So the high volumetric flow rate means the gas goes very fast through. There is not much time for the particles to go to the, or to deposit to the surface. One very important number is not in this equation. Really weird. What is not in this equation? The length, the diffusion. Now the Reynolds number we don't need because we already say, okay, we have laminar flow And we have somehow the velocity in the here, okay? But what is surprisingly not in there? Based on this equation, it does not have an influence. Yeah? The size of the particle is in one number. In which one? What changes with size of the particle? Yeah, right? Diffusion. So here is more or less the size of the particle, because this will change. But what is not in this equation? It's really weird. The time is for the volumetric flow rate somehow, or you can calculate it for time steps. Yeah? Yeah, the diameter of the tube. The diameter of the tube, so how many particles you catch is not depending on the diameter of the tube. Why? What happens if you again, which model are you considering? So you look at this equation and you look at this picture, and now you think, okay, but there should be a difference if my channel is like this or like this. But what happens with these things if your channel width increases or decreases? What changes? Yeah, what happens with my flow rate if I decrease the width from here to here? Decreases? What happens? Increase, right? So if I make the walls closer to each other, the particles will much faster diffuse to the wall. The distance is, right, think about the picture, x is decreasing, but your volume flow rate is still there and it has to go through, so it will go faster. And these two things will cancel out each other. So if you have a set volume flow rate, so that's important of what you're looking, right? So you have a flow rate, which is given, for example, by the engine of your motor. It has to go out. And then you think about a large or a small channel. And then the flow rate will adapt to this distance, and this is why it's not in the equation. So with knowing this number, which is very simple to calculate, you can calculate the penetration. What is meant by penetration? So you see here, penetration versus deposition particle. What is the meaning of penetration here in this case? It's somehow related to efficiency. Yeah? Yeah, very good. So penetration means the amount of particles entering your tube and leaving. So they are not catched by diffusion. And this is what you want to know if you have your catalyst, right? How many of them will touch the wall? Or a filter, how many of them do I catch? So you calculate the deposition parameter, which is quite easy to calculate, and then you go into this diagram and you take a look and you see, 60% penetration, so I only catch 40% of the particles. For a filter, that's not so good, 40%. So you have to adapt on 1, 2, 3 of these numbers. For a rectangular channel, it's a little bit different. So you see it's a little bit different behavior. And you also see that here the width now is as a variable in. So these canceling out only works for laminar flow in a perfect tube. In a perfect circle. And because this is not very precise, there are also some empirical numbers, and these numbers is basically about calculating the penetration, so the ratio of what goes out to what goes in. Okay, so the efficiency would the other way around, so it's, and then you have two equations because it's a quite complex system you look here, so you see them, both of them are empirical fits. And we have different equations to describe this weird behavior here. and this depends on your deposition parameter. So you calculate the deposition parameter, and if the deposition parameter is larger than 0.009, you can use this equation. If it's smaller, you use this equation, and then you're very precise with less than 1% error. You can calculate how many particles will go through your system. Okay. In the slides, I have an exercise example where you do these calculations. I will upload it, then you can try it out till next week. So I think it's a good repetition. You don't have to make the derivations, you just have to calculate a little bit, but you have to use the table and the equation, so the diagram and the equation. So I think it's a good exercise to repeat what we did here. It will not take so much time, but I think it's a good example. And now I would, and then there is something, the last to this part is what called diffusion batteries. So this is systems which basically use diffusion as a separation mechanism. And these diffusion batteries, they have different shapes. So this is basically the case we have on the board. And then you also can have it with just rectangular channels, or this is like sieves. Okay, so you have a mesh similar, from sieving, okay? So it's not that this is spherical and this is somehow diamond. No, it's like a complete different. And what you do is you measure the concentration at the inlet and outlet for your system, and with this you can calculate diffusion coefficients. Okay, that's a very, very good way to get diffusion coefficient or deposition numbers for your system. Okay, because concentration measurement is very easy. And the penetration you can calculate, you can measure very simple what goes in, what goes out. That's not so hard. But getting these numbers, right? So, and there you get these numbers for your aerosols. Then for the last 10 minutes, I will go to another application. And this is basically the sum up for what we did in the last 4 lectures, and this is how filter properties or how filter works. So basically the purifying filters for a room and the one we had on the mask are the same. And these are glass or fiber filters. So if you take a look, you have 20 microns. And you see there are these glass fibers, and there are a lot of meshes, a lot of holes. Do they filter particles which are larger than the pores or smaller than the pores? You see, this filter has a lot of fibers, and the pores are in the range of 20, 30 microns. So does this filter catches larger particles than 30 microns, or also smaller particles? What do you think? Why?
Because the particles which are smaller than the pore size, they get inside, but pass through the whole thickness of the filter.
Because they have to go zigzag through it, right? Yeah. What else? That's right. So it's not that you have a channel like here, but it's really random, so they have really to go like a labyrinth through it. What else?
Bigger particles make a filtrate
Mm-hmm.
bridge, so they will some smaller particles move.
Yeah, but this is surface filtration. This is when you have a filter cake. But I don't know if you saw on your face mask a filter cake on top. So what we have here is depth filtration. So you have a filter, textile, and the filtration will happen in the filter, not outside the filter. I mean, if you have very big ones, of course, they will not enter. But what happens with the particles going through this fiber labyrinth? Yeah?
So, as we consider this filter layer by layer, so the layers are randomly arranged.
Mm-hmm.
So when we have a large hole,
Mm-hmm.
behind that we may have a small
Mm-hmm.
hole. So
Mm-hmm.
it cannot
That's correct. So, but still think about the concepts here, right? So, I mean, of course, when you have a large hole and the particle is small enough to go through, and then there is a smaller hole, it will be stopped there. But is this the main principle of a filter? And this is really important to understand how everything, how the filter works, you have now on the table, basically. And it's correct what you're saying, but the filter not only works in the way, it's not sieving. Sieving means the particle is larger than the pore. Okay, so if you're playing with sand and you sieve it, the ones which are larger than the sieve will stick, the smaller ones will fall down. Of course you have this here, but this is not the main principle of a filter. Yeah?
I think first the filter stops bigger particles
Mm-hmm.
and some smaller particles pass through.
Mm-hmm.
But smaller than certain value will diffuse in the fibers.
Very good. Exactly. So everything we did here applies to this filter. You also want to say something? Yeah. Yeah, exactly. And this is why it's so important to understand these mechanisms. And we had a lot of discussions with the face masks in the last year. And it depends, I mean, every country had different regulations. Germany was very strict with the regulations. And at the end, if you wear a mask or not, I mean, you can decide if you want or not. But what you have to understand is that we know how a mask works. Okay? We know this. We can predict this, and we can compare it to experiment. And I gave you the theory how a mask works. Okay? And if you don't want to wear a mask during a certain time, you will find your reasons, that's fine. But don't think they don't work. Okay? So, because we had a lot of discussions that, for example, here we had people had to wear masks by law, and then people were very creative because they say, no, these things don't work, and they come up with ideas. And then we get more stricter and say, okay, you have to wear at least FFP2 mask or a surgical mask. And it was really hard to convince them that a mask, or how a mask works, or at least that we know how a mask works. And you see, it's not so easy, because from first point, you think about sieving, right? And then you think, these small viruses, how should they be catched by these pores? Okay, let's take a look. So what we want to figure out is the penetration of the particles going through, right? So we have a mask, and we don't want that any penetration happens. So we want all the particles being stopped by the mask. Virus, droplets, everything. So we look at penetration, and penetration is 1 minus efficiency. And the efficiency of the mask is, or here it's for one fiber, okay? Because a mask is extremely complicated to calculate, but we can take a look at one filter, one fiber. It's a quite simple system. We assume laminar flow. And then we just have alpha, efficiency sum, pi 4, and df. df is the diameter of the fiber. So I look at one fiber in my mask, and I know this diameter. 1 micrometer, 2 micrometer, whatever. Alpha is something I also know quite simple, because alpha is the fiber volume divided by the total volume. Basically, it tells me how many fibers I have in my volume. Okay, if I only have one fiber in a volume of 1 cubic meter, alpha is extremely low. And when alpha is extremely low, the particles will go very easily through it. If alpha is very high, I have a lot of fibers. They will catch a lot of particles, but maybe breathing is not so easy, right? Because if I have everything completely full, and sometimes if the mask sits perfectly, you really see how it moves, right? So you don't want to have alpha too large, because then we cannot breathe. On the other hand, we have the efficiency, and the efficiency here is just a sum of different mechanisms. So we have different mechanisms the mask uses to separate particles out of the gas flow. So the big question is how to determine the efficiency of a single fiber, because the rest is very simple to calculate, and then we can, at least for the model, calculate how a fiber would, or the efficiency of a fiber. So therefore, we have to look at the different mechanisms. So this is a cross-section of a fiber, okay? So I have my fiber like this, and I'm looking from this side. So my flow goes over and below the fiber, and you see that the flow has trajectories, right? The streamlines here, the streamlines of the gas. And the first one, and this is what you mentioned, is if a particle is very large, even if it's not larger than the pore, right? If it would be small enough to go through the gaps, it could be still large enough that it's not that agile, okay? So because if it's on one of these streamlines, which directly point to a fiber, the streamline goes around the fiber. The molecules just go around. But the particle has a certain inertia if it's large. So it cannot fast enough adapt to the movement, okay? So you go towards a wall and you only have a little bit time to go to the left or right. And if you're a big particle, you're not able to do it. If you're a small particle, you can do it, okay? But this means this is one of the effects the mask uses. The particle is not larger than the pore, okay? So it means if the particle would be on this streamline here, it would go through because it doesn't have to move. And the important number here is the Stokes number. Do you know what is the Stokes number? Who has heard about the Stokes number before? For sure, anybody. The Stokes number is the ratio of the stopping distance to the, fiber diameter. The stopping distance is something we didn't really discuss here. It means, but basically it tells you how fast can a particle adapt to a movement, to a change of movement or direction. Okay, so how fast I go in this direction, how fast can I go to this direction? This extremely depends on size. The Stokes number is also important when we have volcano eruptions. And then airplanes sometimes are not allowed to fly, right? So what happens is in the engine, you calculate the Stokes number because there you have the wheel in the engine, or how to call it, is moving. And this will separate aerosol particles. And if the concentration is very high and your Stokes number is not so good, you tell, okay, this airplane should not go up, because if it goes up, it will in the engine collect so many aerosol particles till it's stuck. The engine is stuck and then it could not work. This is why airplanes sometimes are on the ground when aerosol particles are coming from volcano eruptions. Okay, so this is basically what you have here. You had a question? Yeah, but there's also a velocity in it. So time, velocity divided by fiber diameter. Okay, and the time is basically the time the particle needs to go left or right or to change the direction. Ku is, J is an empirical number, and the Ku is like a hydrodynamic factor which basically cancelled out because we have one fiber, but in the mask you have more than one fiber, right? And this changes the flow field compared to this picture, and this is considered by these Ku. Okay. So this is the first one. Then we have interception, and interception means your particle is fast enough to adapt around. So it basically stays on the streamline. But if it has the right size, it will touch the fiber. And we said, once it touches the surface, it's out. This counts here also. So the larger the particle, the farther away it could be from the fiber to still be catched by interception. Okay, pure interception, the calculation you see here, alpha is the what we had 2 slides before, R is the ratio of particle diameter to fiber diameter, and we don't have any diffusion or anything else, so pure interception just means the particle travels with the streamline, and if it has the right size, it will anyway touch the fiber, and then it's out, okay? And here you see interception in an experiment. So this is a fiber. And now we're looking like this on the fiber. Okay, so in the picture before we looked from here, and now we're looking from here. And then soot particles are just going through. And it's not so easy to make this experiment, but you see it's with long time, but with long time, I mean, the concentration was not very high. Here, it's quite slow concentration, very slow, low concentration. But you see that more and more particles are catched, and here basically the assumption that the particles are cancelled out is not a good one, because you see how it's growing and growing, but you see that interception really works in the way as we see it in this picture for a given particle size. And then the last one is diffusion. Because it could be that a particle starts on a streamline which would not hit the fiber. But the particle moves anyway because of diffusion. So there's a chance that the particle here, which is quite small, because of diffusion is important for small particles, so it would go with this streamline, and if it would go with this streamline, it would never touch the fiber. So no interception. And it's so small, so no impaction. Okay, so because it can go around, small enough for it. But diffusion. And diffusion just means it moves in any way, in any direction, random. So there is a chance to hit the fiber. The more fibers, the more volume or area of the fiber, the higher the chance. Okay, so if you now take a look at this image, a lot of surface area, lot of chances to win, in this case, to hit. So diffusion is extremely important. It basically is the main mechanism in small scales of particle transport. And with the equations you see here, and this depends on the Peclet number. The Peclet number is something similar like the Stokes number. And but it has the diffusion in it. The Stokes number doesn't have the diffusion in it. And with the equation I showed you, you can make this diagram here. And this diagram is the filtration efficiency, and it's the filtration efficiency for diffusion, for impaction, and for interception. Okay, so three curves for 3 different equations for 3 different mechanisms. And what can you do? You can sum up them. This is the total efficiency. So we have the filtration efficiency for a single fiber over the size of the particle. And we see that the diffusion, and this is something you should understand now, decreases with size, right? The chance of a particle to diffuse to a fiber decreases with the size of the particle. The other way around is with increasing size, therefore we have interception and impaction, because the larger the particle, the more inertia it has, so the lower the chances to go to the labyrinth, or the larger it is, the much bigger the chance is to stick by going around. And there is just one. What is the meaning of this minimum here? There is a minimum. When we count all of them together, there is a minimum. We still need 5 minutes, but then we are done. So what is the meaning of the minimum? Yeah?
In that size range, the particles are not small enough to diffuse and not big enough to stop by interception and impaction.
Yeah, exactly. So at this size, the filter works the worst. And the worst means around 60 to 70%. So the very small ones, you're nearly 100%. The very big one, you're nearly 100% of them are stopped. But there is a size, and this is called most penetrating particle size. Penetration, okay, right? And this is exactly this size because they are too large to diffuse strongly and they are too small to have big inertia. And you know one size or one example where we exactly have this particle size. What is the size, basically? If you take, where is the most penetrating particle size here? What is the size, roughly? Half a micron, yeah. So it's a log scale, so it's about 500 nanometer, 200, 300, 400 nanometer. What do you think has exactly the size of 2, 3, 400, 500 nanometer? Which particles have exactly this size? Yeah? Colloidals? Nah, coronavirus is here, but it's a little bit smaller. It's around 100. But I want to have another one. Also, the big question with the coronavirus is still there in droplets, right? And I don't know the size of the droplets. And this is, I think, I will show later a paper where they try to sum up everything of this theory, but we need coagulation, evaporation, and so on. And then when there's still the question of the impact of the droplets. Oxygen? No, oxygen has another size.
Even though we don't need the foreign particles, we still need some particles.
Yeah, but I want to have a very specific example here, which exactly has the size of 3, 4, 500 nanometers. And there's a reason why it has the size. This is the reason. Smoke of a cigarette, why? Why smoke of the cigarette can only be in this size? This is why it's so interesting. It only can be in this size. What happens if the smoke of the cigarette is larger? What has your cigarette? Yeah, a cigarette has a filter, right? And if you take a look at the filter, it's a fiber filter. It looks exactly at this. So if the particles are larger, you would not smoke anything. You cannot. Everything is stuck by the filter. And if it's much smaller than 500 nanometer, you cannot smoke anything because it's stuck in the filter. And even if you can say, okay, I can smoke without a filter, okay, but the ones with filter work. And basically, the lung is also like a filter because if you take a look at me, my mouth is here. So the first one, the air and the particles have to do is a 90-degree angle. So, and this is what you see if you have dusty air, you already feel that you catch particles here, right? And this is because of impaction and interception, okay? Because the big guys cannot make these 90%. There's a reason why the mouth is not here. And if the cigarette particles would be much, much smaller, they would go in the lung, but probably not go out because of the diffusion. They would be catched by the very, very high surface area of the lung. So cigarette smoke has to be in this size, and this is why cigarette smoke is so interesting. And this is the theory. This is just calculated from the equation I showed you. And this is the experiment. So here you see the same diagram for FFP2, fabric, and type 2, the masks, and you see it perfectly follows the theory. Okay? So especially FFP2 and type 2, this is the one here for the type 2, you really nicely see the minimum going up and down. And this is exactly what is predicted from the theory. So it perfectly worked as we think. And this is extremely important to understand how to work with science and scientific results. Because if you decide you don't want to wear a mask, feel free to don't do it. But don't explain to people who know how a mask works that this mask doesn't work. I mean, if you put it like here, okay, it will not work. But the results are quite clear. And the really cool thing is the FFP2 mask even is extremely better. The FFP2 mask doesn't have the minimum. Why? The minimum is gone for the FFP2 mask. How does you get the minimum away, right? So there seems something happening which is not in the calculation here, but makes this difference here. It's not the size of fiber, but it has to do with the material of the fiber and the properties of the fiber. Did you figure it out or have heard that from time to time you should put your FFP2 mask in a furnace? And you should not wear the FFP2 mask too long. You should replace it from time to time, right? But I mean, if it really breaks, you see it. But generally, I mean, you can wear it, and this is a static effect here, right? So there is no, as long as the mask is still working, there's no reason. But what happens is that a mask is charged because you don't have conducting material. And this charging of the mask helps you to get rid of the minimum. Okay, so the effect from here to here is electrostatic you have on the mask because it will repel. But your breath has a certain humidity, so it will wet the mask. And when the mask is wetted, these charges will go out. And if you put it in a furnace for half an hour at, I don't know, 60 degrees, the humidity will go away. And then you just make it like this, and you have like this, and then it's charged again, and then the minimum is gone. Good. With this, we are finished for now.